Before we write a single line of code, let me show you what we're building. I type a question about research papers I've never read, and in under 3 seconds I get an answer that cites the exact paper and page number. This isn't ChatGPT guessing. This is grounded retrieval from my own documents. Now let's build this, step by step. Last video we walked through this architecture. Today we code every single box on this diagram. Document loader is step 1, chunking is step 2, embedding model is step 3, vector database is step 4, and the query chain, retriever plus LLM, is step 5. 7 dependencies, 70 lines of code, and a fully working RAG pipeline. Let's go. Things to set up. Dependencies, a free Pinecone account and your API key. Pinecone's free tier gives you 100,000 vectors. That's enough for thousands of documents. Sign up at pinecone.io, grab your API key, drop it in a .env file, and you're ready. 1. Load the documents. We have 10 research papers in a PDFs folder. LangChain's directory loader reads every PDF in one call. Each page becomes a document object with 2 fields. Page content holds the text and metadata holds the source file name and page number. That metadata is what lets our final answer cite specific papers. 2. Chunking. You can't embed an entire page. It's too large and you'd lose precision. Recursive character text splitter splits our 247 pages into bite-sized chunks. Why 512 tokens? We covered this in video 1. Too large and irrelevant context sneaks in. Too small and you lose meaning. 512 is the sweet spot for research papers. The 50 token overlap ensures we don't split a sentence in half between 2 chunks. 3. The magic step. We convert each chunk from text into a vector, a list of 384 numbers that captures the semantic meaning of that text. We're using All-Mini LM L6v2. It's free, runs locally, and produces 384 dimensional vectors. This is the model that makes termination clause and end of agreement look similar, even though they share 0 keywords. That's the fundamental advantage over keyword search. 4. Store all 1,147 vectors in Pinecone. First, create an index. Then, one line to embed and store everything. Dimension 384 matches our embedding model. If you use a different model, you need a different dimension. Get this wrong and you'll see a dimension mismatch error. Cosine metric works best for text similarity. And serverless means Pinecone handles all the infrastructure. 5. The moment of truth. We build a retriever, a prompt, and chain them together with LangChain expression language. And there it is. The retriever searches Pinecone in under 20 milliseconds, pulls the 4 most relevant chunks, injects them into the LLM prompt, and the LLM generates a grounded answer, not hallucination. Cited facts from your own documents. 70 lines of Python. Mistakes I see engineers make with every RAG pipeline. Mistake 1, dimension mismatch. You create a Pinecone index with 1536 dimensions because you copied an OpenAI example, but you're using Mini LM, which outputs 384. Pinecone throws a cryptic error. Fix. Always match your index dimension to your embedding model. Mistake 2. Chunk size too large. You set chunk size to 4096, thinking bigger is better. Your retrieval results become terrible. Fix. Start with 512, tune from there. Mistake 3. Forgetting the API key. You get an authentication error and spend 20 minutes debugging your code when it's just a missing environment variable. Fix. Always use .env. Improvements to take this from demo to production. Caching means repeated queries are instant. MMR, maximum marginal relevance, gives you diverse results instead of 4 chunks that say the same thing. And metadata filtering lets you search within a specific document. These are the production upgrades that separate a demo from a real product. Built a complete RAG pipeline from scratch. 10 research papers, 70 lines of Python, and you can ask any question and get a cited answer in under 3 seconds. Let's recap. PyPDF loader ingests the documents. Recursive character text splitter chunks them. Hugging Face embeds them for free. Pinecone stores and searches them. And LangChain chains it all together with Ollama running locally. Total API cost, 0. All the code is on GitHub, link in the description. Subscribe to Neural Scale for more.